Now, okay, so this is the outline. So a brief introduction. Then I'm going to talk about in this divided the talk into two parts. Part A, so how to electrically detect and manipulate the static antiferromagnetic order parameter in chromium oxide. And the part B, I'm going to focus on the Magnon transport and how to understand the effect of a spin disorder on Magnon spin transport in chromium oxide. Okay, this slide I used a few years ago, and the motivation remains the same. So we were all excited by the unique benefits of using antiferromagnetic material for spintronics application, just like using ferromagnetic materials for the current technology in spintronics technology, but antiferromagnetic offer many more attractive benefits. So I don't have to go to detail for this audience. And the many excellent research, review articles have been written. I'm not even including the recent exciting research in non-collinear antiferromagnets and automagnets. I want to stress that because of many experimental challenges, the experiments are lagging behind. So in this talk, I just pick a very fundamental topic. One is a research topic. One is how to reliably to electrically detect antiferromagnetic order parameter for operation of reading and writing. Then another question I want to address is how robust is the Magnon transporter against the spin disorder? We want to transport the antiferromagnetic Magnon information presumably to a longer distance, but how do spin disorder affect such a transport? Okay, broadly speaking, antiferromagnets, the class has so many members and ranging from oxides, fluorides, and many others. And a lot of them, most of them are insulators. So on this slide, I believe a few examples, right? So example, manganese telluride and manganese difluoride, these two also a member of automagnets, right? So I'm using them and the nickel oxide to show that there are some relatively simple in terms of the spin or domain structures, simple materials as opposed to others. So in this talk, I actually choose the simplest material, that is the uniaxial antiferromagnet, meaning that the easy access is either along this particular direction or opposite to the direction, or up or down. So somewhat this manganese difluoride has this simple uniaxial properties in the anisotropy. Okay. Also, in general, to probe static antiferromagnetic order in bulk materials, one can use thermodynamic probes such as the magnetization, susceptibility. In K-space, one can go to neutron facilities to do neutron scattering or inelastic scattering. So scanning probe in some labs, there are specialized probes to do electron scanning, electron or STM. Most recently, scanning MV imaging to image local straight magnetic field in a very sensitive fashion. Some other techniques that are also very powerful that also specialized. So one of them is using synchrotron X-ray, so linear dichroism to do PIM imaging. And And even earlier than this, much earlier in 1990s, and using second harmonic generation, particularly suited for chrome oxide. And recently, the second harmonic generation was used to probe few layer 2D antiferromagnetic layered materials with a relatively high sensitivity, spatial resolution, and sensitivity to magnetism. Okay, so here I like to focus on electrical detection because for any potential applications, one has to read out information very quickly, and presumably also you want to write, you want to manipulate it. But the first thing is to read the antiferromagnetic order parameter. Okay, in metallic antiferromagnets, of course, one can resort to the Hall effect or anisotropic magnetoresistance and planar Hall effect. But for insulating antiferromagnets, we have to use some metallic layer, right? So to sense. So a metallic sensing layer is needed. So there are two types of metallic sensing layer. One is to use ferromagnetic sensing layer, so to take advantage of the exchange bias effect. So, so the magnetization or using MOC or magnetometer, this is a very well established technique. So people have, used the technique to measure the shifted hysteresis and to trace back the state of antiferromagnetic order parameter. For electric detection, one has to use anomalous Hall effect and anomalous and anisotropic magnetoresistance in the metallic magnetic sensing layer. So for the other class is non-magnetic sensing layer using heavy metal or any other material with a strong spin orbital coupling. So there are two types of effect. One is using the SMR, the spin Hall magnetoresistance, and the Hall effect. And there's a negative, in general, it's a negative SMR. So a lot of people have done studies in the past a number of years. And I only included here an incomplete list of the researchers. And the other type, actually, I like to stress in this talk is something called a spinning current anomalous Hall effect that was pioneered by in Kosup's papers, at least the two papers I highlighted here, and in other some other places called the zero offset anomalous Hall effect. So I'm going to almost exclusively focusing on this technique. Okay, so just to quickly summarize, so we're looking at the Hall effect detection because it doesn't contain magnetic sensing layer. So the one downside of using magnetic sensing layer is that eventually, if you want to do a antiferromagnetic spintronic applications, you do not want to slow down because of the ferromagnetic. You want to use the ultra fast properties of antiferromagnetic material. So, and also needs to be easily implemented in the circuits. So I think that this detection has advantages, this Hall detection. But one challenging in all this method is that one needs to be sure that you're reversing the entire structure that you're probing. And some method, for example, exchange bias, you have a shift and loop, but you don't know whether it's the whole structure or a small part of the structure. So you will get a minor loop, but you don't have full knowledge of the entire structure. So I want to stress that we need to actually make sure that we have a single domain state. We want to read off the nil vector of the single domain state, whether it's reversed or rotated. Okay, so as pointed out many years ago by Benek's group, so chromium oxide chromium oxide has a very interesting spin structure, relatively simple. But if you look down along the C-axis, the top layer, the spins behave like a ferromagnet. So the spins are all align up. So this moment here, the surface moment, can be detected by MOC, which is a surface sensitive technique. So this was proposed as a unique way of probing the uncompensated moments on the surface using the induced anomalous Hall effect in platinum, for example, and other heavy metals in principle. So as I mentioned a little earlier, so the multi-domain, if you have a multi-domains, the signal will be weaker because there are up and down cancellations across different domains. So this we need to be mindful when we prepare the material. Okay, so here's the essence of the technique. So you have a very simple cross. Let's say it's a Hall cross, very simple structure. This is the platinum or sensing layer on top. So X direction and Y direction. So if you pass current along X direction, you measure the Hall effect along Y direction, then you rotate your current by 90 degrees. Likewise, the Hall voltage will be measured in this fashion. Then when you do that, you do the sum of the two Hall signal. Then you get rid of the asymmetry induced by geometric imperfection. So if you're an experimentalist, you know when you hook up a device to measure the Hall effect, even though you think your device is symmetrically defined, you always have some non-zero signal. But doing this, you can get rid of that signal, spurious signal that you don't want. So I like to just generalize a little this technique a little bit, one step further. If you detect a spin flock, for example, spin flock transition of antiferromagnet, in this case, chromium oxide, you have the top layer moment transition from up to horizontal, right? The vertical direction to horizontal. So when you have this moment here, horizontal moment, depending on the orientation in the plane, the projection in the plane, so you also have a planar Hall effect. So how do you separate this effect? But it's a very interesting way. So if you do the sum, you do this spinning current measurement, you do the sum, and the in-plane component will produce opposite signal in the two Hall channels. So these two, if you do the sum, and the planar Hall effect will be canceled out, so that you can do the sum to get rid of the planar Hall effect and as a geometric, the asymmetry effect. But if you do the difference, then you do get the planar Hall effect. You can separate. But there's also symmetry induced. But that presumably would be much simpler. When you change the magnetic field, you're looking for some characteristic that you don't expect from the asymmetry induced artifact. Then you get the planar Hall effect. Okay, I also want to point out that in the planar Hall signal remains the same when the in-plane moment or the Néel vector reversed by 180 degrees. So planar Hall effect cannot distinguish the reversal of the in-plane moment or in-plane Néel vector. So with that, I started with 50 micron platinum, 50 micron each way in the Hall cross. So this Hall signal, after I subtract the ordinary Hall effect, which is easy to do, I'm left with this red and blue, the two curves. And when I sweep a magnetic field along the C-axis. I'm sorry, this is also the C-axis. So I induce, sorry, C-axis. So this I'm using this field to induce a spin flop so that I can check the nil vector rotation, right? The transition from the up and down to the lateral to the horizontal. So this transition is the spin flop transition at the 6 Tesla for chromium oxide at low temperature. Okay, so as I mentioned earlier, if we detect the planar Hall effect, these two channels will report opposite polarity. So this is exactly what I see. When I have the spin flop transition, one channel I detect upward jump, the other is opposite, right? These two actually look very symmetric. So that means I'm detecting primarily the planar Hall effect here. Okay, so spin flop occurs at 6 Tesla. Oh, I'm sorry, this material is a bulk material. The thickness here is around either 500 micron, half millimeter. Some crystals I have a 1 millimeter thickness. So this type of material, bulk crystal, have very well defined spin flop transition measured in our early work, the spin feedback effect measurement, and also in the spin flop magnetoresistance measurement, we can also detect the same spin flop transition. But here I want to emphasize, here we have more information. Let's say compared to spin flop magnetoresistance. Magnetoresistance can include some other artifacts, such as magnetostriction induced resistance change. Okay, so let me just use these two curves I detect in the two channel. I get, if I do sum, I get the blue. If I do difference, I get the red. So as I mentioned earlier, because this near asymmetry between the two curves, so I have primarily the planar Hall contribution. So red is the planar Hall effect signal. So this, the similar effect was detected previously, reported in a PRB paper by a Taiwan University group, the planar Hall detection. And here the blue, I essentially have close to zero signal, right? There's no clear signal. I mean, at least I'm looking for some abrupt change around the spin flop transition, but there isn't any. So I hypothesize that this region here, we have a multi-domain state. So you have a up-down domains. You have near complete cancellation in this field range. Okay, then outside you have a spin flop. It may have spin flop domains, but my signal is not sensitive to either in the planar Hall or anomalous Hall. I'm not sensitive to that. So I have a multi-domain up and down below the spin flop transition, and a spin flop domain possibly above. Okay, speaking of domains, there are many ways of detecting, but for ferromagnets, for antiferromagnets, there are limited techniques available, right? I just want to show that the second harmonic detection was included, one of the early slides. So the optical, this is magnetic circular dark horizon imaging. So whenever you use a light, unless you use a scanning probe, so you're limited by the diffraction. So the spatial resolution is not that good. But luckily for bulk chromium oxide crystal, the domain size typically is large. Okay, millimeter or smaller, right? So for thin films, the recent studies one of the papers, a couple of papers published just last year. So this is a very interesting paper published by Dresden Group. They patent structure, antiferromagnetic chromium oxide actually structure, showing very rich, fascinating domain structure. Okay, so there are other domain studies in other materials. So we may live with domains, existence in domains in antiferromagnets. This is something very different from what we imagined like decades ago. When we talk about ferromagnetic domains, we always blame the dipolar interaction, right? It drives the domain formation. But here in antiferromagnets, we also have domains. They stop, right? So one way of showing this effective domain is to reduce the sensing to the device size. So I reduce the size to 10 micron cross in each dimension, X and Y dimensions. So the anomalous Hall in these two channels, the two perpendicular orthogonal channels, one again red and blue, you see now they're not opposite to each other, right? So they're jumping to the same direction. That's immediately an indication that I have something, an anomalous Hall signal included in this, right? Okay, so if I do a little bit more, so this is the zero field cool from above nail temperature, which is 307 K. So I cooled from 320 K. So zero field cool, and I perform field cool, but with a positive field, 1 Tesla. Then another cooling, I use a negative field cool. So these two field cools produce this in two channels. I use the same color code as the left. So you see the zero field cool is, the trace is almost identical to the negative field cool, but opposite to the positive field cool. That is very interesting. So if I do sum and a difference, meaning that the red should be the planar Hall, the blue should be the anomalous Hall. By the way, the ordinary Hall effect is already taken out. So I immediately see something. Okay, the cooling field has the ability to at least to alter the nail vector orientation. Okay, so different field cool produce a different result. Secondly, I think the most important, more importantly, is the nail vector in the zero field cool choose one of the two orientations. As you see, the zero field cool actually, in this case, chose the negative field cool, the state, because they're identical. So that's the indication that maybe the 10 micron device, I'm sensing single domain, at least a single domain region. Okay, so there's, the signal, the anomalous Hall signal has some asymmetry that I'll discuss on this slide. So if I take the sum signal, that means should contain anomalous Hall signal on the left. Then apparently, so I have three traces, meaning zero field cool, positive field cool, and the negative, this is the positive. The one of the trace is negative and the other is zero. So apparently there's some signal there is not changing when I flip the nail vector. So I take the difference between these two. I get this middle. The middle is field antisymmetric signal. So it doesn't change as I flip the nail vector. Okay, this part, this signal is always there. I'll show you different devices, but its origin is not completely understood. If anybody has any idea, I will be very happy to discuss with you. And if you get rid of the antisymmetric signal, then I'm left with the nice looking, the symmetric signal that does flip when you reverse the nail vector. So this is basically the domain completed reversal and spin flip domain on two sides. Okay, so it's sensible to check whether this is true in smaller devices. So previously we used a photolithography to define those devices. Now I'm using the electron beam lithography to pattern devices from 10 microns down to 0.1 microns. So here I choose 4 different dimensions on the left. So you see that the 10 micron device is actually, the behavior is very similar to what I showed earlier. So 1 micron, 0.5, 0.1 micron results are shown on the right. So here, so as I mentioned, this anti-symmetric features still remain, even down to 0.1 micron. So we believe that's a real signal. Then the symmetric part is simply very well-defined steps at the transition, the spin flip transition. But if you look at the middle one, the 0.5, if you just look at the positive field cool, I produce this upper curve in the middle. But if I use, okay, these 3 devices are located on the same crystal, different locations, maybe separated by hundreds of microns. Okay, so this device has a positive signal when you do positive field cool. But in hundreds of microns away, the other device, 1 micron, has a negative. I'm sorry, negative is right there, the blue. You should look for blue. Negative, and also 0.1 micron is also the lower branch, the negative, right? So that tells me that the whole device, if you do field cool, you do not set the whole crystal into a single domain. So different parts, you have a different domain, different, some up, some down. But if your device is small enough, you sense small regions that is a single domain, but no guarantee you're in the up or down orientation state. Okay, so another thing, a very important message is if you scale, if you do everything properly, then you look at the 2 responses, right? The positive, negative Néel vector states. The anomalous Hall magnitude from down to up remains about 6 milliohm. It remains constant in different devices with 2 orders of magnitude difference in the device size. I mean, the linear dimension from 10 micron to 0.1 micron, this difference remains 6 milliohm, about 6 milliohm. That means you are really sensing the single domain state. So this, I'm going to skip this slide. It's just a temperature dependence, and the largest signal occurs around this temperature range, so 8 milliohm or so, the largest response. Okay, let me summarize the first part. I hope I have facts to show you that we are able to electrically detect both in-plane and out-of-plane components of the Néel vector. In principle, this is almost 3D, but in the XY plane, there is a 2-fold symmetry. So it's not quite 3-dimensional, but we are able to detect these 2 components of the Néel vector. And we can manipulate, for the reason that we don't complete know, we can manipulate Néel vector state by magnetic field only. We also did separate study using gate voltage, so using the magnetoelectric effect. This effect has been demonstrated by many researchers already. So we can actually uniquely set the Néel vector to some state more deterministically. Okay, so second part, I'm going to focus on Magnon transport in antiferromagnetic chromium oxide thin films. Actually, both thin film and the bulk. Okay, so we a few years ago, we know that some phenomena reported long distance antiferromagnetic transport phenomena was reported in different material systems, including chromium oxide already, chromium oxide thin films, and iron oxide, and also the multi-gated graphene, the quantum Hall canted antiferromagnetic systems. So no matter what mechanism drives this phenomena, the common message is that antiferromagnetic insulating state can transport Magnon information over many long distance, as long as microns or longer, depending on the material system. So key questions we want to ask, okay, these materials were made to have, high quality with less defect. The defect configuration is a set one, right? There's no way to control or systematically to vary the spin disorder. So we like to study the effect of spin disorder on the Magnon transport to see ultimately how long the Magnon can transport. Okay, so one technique we use is the spin-SPICE effect. So we noticed earlier in our 2020 paper, Nature paper, we noticed that the surface, so smooth surface, this is the bulk crystal again, and intentionally bombarded surface with ion. Okay, so we see that the generic, this is the, okay, let's look at the lowest temperature, and the signal actually, lowest temperature is blue, and the signal, it looks very different from the same crystal, but the surface bombarded by energetic ions. So now you see the huge difference. The slope, even the middle, the slope is changed from positive to negative. So we really need to be sure that what are we detecting? Are we detecting the intrinsic Magnon spin current, or we're detecting some extrinsic signal? I mean, by extrinsic meaning by defects or other unrelated to the bulk magnons in the bulk crystal. Okay, so this notion was pointed out earlier by one Argonne group, and that the specific actually is sensitive to surface in their measurements. So we did a little more study on this. So we polish and repolish a crystal different times. Actually, we have more than 3. I just want to show 3 curves here. So the only parameter we're tracking is the surface roughness, the RMS roughness measured by the atomic force microscope. So we have this same crystal, but a different roughness. This is the only parameter we see as the roughness increases. So the curve changed from the blue to black. So as the roughness changed from 0.2 nanometer to 0.5 nanometer. Okay, this is a very clear that some extrinsic factors play some important role here. Okay, the rougher surface, we have this overall background. You see you can view this, the blue curve is nearly intrinsic, let's say intrinsic signal is riding on some background, which I'm showing here. So in order to see this background, we fabricated this is the easy axis configuration. So apply field along the z-axis, along the c-axis. Then I measure this specific signal in the channel perpendicular to the c-axis, to the field. So the other case is the hard axis configuration that we applied field perpendicular c-axis. In this case, we do not induce spin flop transition. You see here in the hard axis, we see a larger signal, the background. The hard axis is a configuration that we do not see abrupt spin flop transition. Instead, we see a continuous, this is a smooth transition in three different devices that we studied in the z-axis situation, right? So on the other hand, if we just do a simple simulation, just considering the Magnon in the bulk, the Magnon transport in the bulk crystal, the red curve is the z-axis signal. You see, z-axis signal after the spin flop transition, it locks to a very small level. This nearly zero, right? But a small, in this case, negative across zero, right? But a small negative signal. But this is the case, actually, the blue is the hard axis signal. Hard axis induce canting, but from zero to high field, the whole range, the signal remains small. This is clearly by comparing to the simulation results, we conclude that there is defect in the roughness induce some kind of background. And the inset shows the simple Brillouin function fit. So this signal can be modeled by just paramagnetic response. Okay, so what do we do now? What do we do here is take the difference between the two. So we measure, just alternate the orientation of the field, the both z-axis, hard axis. What do we get? We take the difference, we get a signal like that, okay? The blue and the green look similar, look closer to what is predicted or calculated in our the slide I showed earlier, the simulation result. And that's good. The first order effect is taken out, which is antiferromagnetic, the paramagnetic contribution is taken out. But we are left with a secondary, probably more interesting effect. The effect you see here can be highlighted by this black curve. The black curve is the roughest one. Okay, we don't have, at this point, we don't have other parameter to describe this sample. It's a 0.5 micron, 0.5 nanometer roughness. So you see this one, what is strange about this, you lose the sharp spin flop transition. That means you have something more than the addition of the paramagnetic contribution, right? Your spin flop transition now is broadened. But on the other hand, I still have the bulk crystal under the rough surface, right? So this is raised interesting point. So what do we do here? We want to use well-controlled, at least to get rid of the surface roughness by growing atomically flat surface of chromium oxide. Then we want to control the spin state ultimately, right, to spin disorder. But first, we want to grow structurally sound, structurally and morphologically good surface. And then we create this surface, want to see the effect of the Magnon transport, effect on the Magnon transport. So we use a PLD to grow atomically flat aluminum oxide. In this case, the chromium oxide on aluminum oxide substrate. So as indicated by the read pattern, data, and X-ray ex situ, this is the in situ, ex situ, as indicated by the X-ray reflectivity in the red, and also the high angle Bragg peaks. See oscillations indicating high degree of surface flatness and also the structural coherence. And TM confirmed excellent layering. Across the interface here, the chrome oxide has well-defined layers, but we also see the regions with contrast variations in the TM, right? This is something I want to talk about it later, okay? So what do we do here? So we do spin feedback measurement. I will call the chrome oxide film grown on aluminum oxide, called this heteroepitaxial film. So I show you two examples here. So the red one is the 12 nanometer film. The other is 3 nanometer. But 12 nanometer films, you see this spin flop field I kind of expected from the bulk measurement I showed you earlier, which is 6 Tesla. Now is significantly extended to the high field, the spin flop. And on top of that, I have a much broader, is like one order of magnitude at least broader distribution in spin flop transition. So this is what I see in the heteroepitaxial film. So one may ask, okay, you have a lattice mismatch, you induce some strain, then it will have some effect on the heteroepitaxial film, or chrome oxide film. But how about homoepitaxial film? So we grow chrome oxide film on top of a crystal. The crystal is prepared with a smooth surface with the RMS roughness less than 0.2 nanometer. So we grow, and many films, here I pick this homo, which is a red, 14 nanometer homoepitaxial films grown on chrome oxide crystal. Now, I have the black one as a reference. Okay, you see, these two essentially, the thickness about the same, right? 12 versus 14, have same characteristics, broadened and upshifted the spin flop transition field. So this is a very surprising. That means That means the interfacial lattice mismatch does not play a role, or at least not the primary role here. Okay, so we know that spin flop transition is broadened. This means we have a distribution here. That means it can be only caused by spin disorder. By spin disorder means magnetic property variation locally, right? You have a lot of variations in the film. Okay, so if I do different film thickness, this is a homoepitaxial film grown. The black dots are on chrome oxide crystal, and also included the heteroepitaxial films. So spin flop transition as a function of thickness and has this overall trend. When I grow thicker and thicker, actually, the spin flop transition is shifted to a larger field. Okay, so now what I want to understand is, okay, how about I have a well-defined crystal with polished, smooth surface, but I inserted one layer epitaxially grown chrome oxide film. Then this film, I know the characteristic of the film already has a broadened and upshifted spin flop transition. That means I have some disorder here. By controlling the thickness, I control the degree of a disorder. The reason is a separate story, okay? But I can control that. Then eventually, I use a platinum to detect the magnons coming to platinum, both from the bulk and from the film. From the bulk, presumably I know if there's a magnon current arriving at a platinum from bulk. I know because that must carry the 6 Tesla jump, the spin flop jump. Okay, when the spin flop occurs, I would have a jump. So this 6 Tesla jump must be there. But if I don't see that, I see a rather broadened transition, spin flop transition, then I don't see the bulk spin current coming from the substrate. Okay, this is what I see here. So the black curve, it's a busy slide, but the black curve is no epitaxial film of a well-defined transition. You don't see the transition here because it's right under this yellow. The yellow is the 3 nanometer. If you put only 3 nanometer of chromium oxide film, then the transition, the spin flop transition, is still at exactly at a 6 Tesla. So that means the 3 nanometer makes no difference, very little difference to the Magnon, bulk Magnon transport. The same Magnons can cross 3 nanometer chromium oxide film and arrive at the platinum detector. But we lost the 6 nanometer ones, but here the next thickness is 9 nanometer, which is the blue. This blue, you can tell there's no feature no jump, downward jump at a 6 Tesla. That is an indication that the bulk magnons cannot arrive at the platinum. Okay, so somehow at 6 Tesla, between 3 nanometer to 9 nanometer, we lost the 6 Tesla feature. That means we lost magnons coming from the bulk. So that is very surprising to us. The distance, such a short distance, the magnons can travel, the bulk magnon can travel. So we're looking for possible causes of the spin disorder. So first, we only have a structure characterization here. So on the left is the high resolution TM. You see TM, as I showed earlier, on a heteroepitaxial film, there are small, regions that, have a faint, the contrast variation. But otherwise, the film has well-defined crystal structure. But sure enough, when you do the same experiment inside the TM to detect the X-ray signal, so the EDS, the X-ray energy dispersive X-ray spectroscopy, then we monitor the chromium to oxygen ratio, which is in this red data, the curve. So the overall trend here, the spin flop transition, this is the chromium oxide, the chromium oxygen ratio increases as the thickness increases. So that's also, we also put spin flop transition field in dots as a background. They kind of go in the same trend. The blue is the magnitude of the spin feedback effect. It decreases. Okay, so we observed that the oxygen vacancies developed, okay, as we grow thicker and thicker. That's purely structure, but this structure can be coupled to the magnetic properties through broken bonds, right? Through the coordination number change, and also, macroscopically, we can view that as a magnetoelastic property through magnetic elastic coupling, changing the magnetic properties. So missing oxygen ions cause some variation in magnetic properties. That is the possible cause for the scattering, right? So looks like two relatively long wave magnons. These are subwavelength spin disorder, but they're very effective in scattering magnons. So I'm running out of time. Let me quickly just summarize. So the first part, electric detection and manipulation. So I want to point out that the challenge here, we really need to find a good material that can detect, report large anomalous Hall signal. So this is one part that we need to deal with. The manipulation, right? We have to replicate the results in thin films. So people have done some work, but we really need to be sure that we can manipulate the thin film properties, the neo-vector properties. And the second part, I've shown that spin feedback is highly sensitive to surface condition, and we can break down in this response into paramagnetic background, as well as the part that is more interesting, that is the spin disorder can greatly suppress Magnon spin transport within very short distance. So lastly, I want to thank my students and postdoc and my colleagues in UC Riverside. Thank you very much for your attention.
Thank you. Thank you very much.